Thanks, Joe. I'm going to start on this board with just a preface of generalities. Let's call this the archetypal moduli problem. By which I mean from the perspective of global analysis or differential topology or symplectic topology as distinct from algebraic geometry, where they also like to talk about moduli problems. So for me, a moduli problem means this kind of thing. You have some space, which I'm calling suggestively J, but right now I'm just going to call it the space of data, which has some kind of topology on it. And for each choice, which I will suggestively call also J, in this space, we get some moduli space M of J, which also has a natural topology. And of course, we would like to say that it has some much nicer structure than a topology, like being a smooth manifold, or if we can't achieve that, maybe at least a smooth orbifold. And over the course of these 2 weeks, I'm sure you'll also hear things about weighted branched orbifolds with boundaries and corners, though not from me. From my perspective, well, the first thing to say about this moduli space is that locally you can identify it with some kind of zero set, which I'll write sigma j inverse of 0, except not precisely that. Often you have to divide it by some kind of symmetries. So here sigma j is some section of a Banach space bundle. And we already heard Dusa sketch one example of this. Because you can express all sorts of geometric PDEs in this way as preferably smooth sections of Banach space bundles in an infinite dimensional context. But I'm saying this is true only locally in general. So Dusa described a situation with holomorphic spheres where you can actually do this globally. But in my experience working with J-holomorphic curves, that's rather the exception to the rule. And so I will talk about some more general situations where you can do this but only locally. And these symmetries can cause quite a lot of headaches. But the first problem, of course, is you want to be able to say that this zero section here is a smooth object. And the implicit function theorem ought to tell you that if you do things correctly. But there are two general ways that you can approach that. First, the so-called abstract approach, where you perturb the right-hand side of the equation. You can say something like, define the moduli space M tilde, which depends on the data J, and some extra auxiliary choice that I'll call nu. That's the space of all u in this Banach manifold such that sigma j of u matches nu of u. So this is for some other section nu of that same Banach space bundle. And the idea is if we choose that generically, then this set of solutions will be a smooth object simply by the Sard-Smale theorem. Right? So that's kind of equivalent to the statement, just expressed in local trivializations, that a generic point in the target of a smooth map is a regular value of that map. So this is a generic section, is also intersects this section transversely. So for generic choices of this auxiliary nu, our special section sigma j is transverse to that, which means this moduli space of perturbed objects I define is a manifold. And I even want to say more, because if we're talking about elliptic problems, this section is not just a smooth section, but also is Fredholm in the sense that its linearization at any point is a Fredholm operator. So when we have these kinds of transversality conditions, we get not just a manifold, but a finite dimensional manifold because of finite dimensional kernels of the linearization. So that's, of course, very nice when that happens. The problem is I perturbed my equation to a different one, which might not be the one I'm actually interested in. That's problem number one. There are more problems, which I think you'll hear more about over the course of the 2 weeks, because this abstract approach is sort of the raison d'etre for the whole polyfold project. But it's difficult. And part of the reason it's difficult is that, first of all, this correspondence between some zero section and my actual moduli space of interest is in general only local, and it also has these symmetries. You have to deal with those both of those in a sensible way when choosing these perturbations, and it means just choosing some generic section of a Banach space bundle is usually not enough. You have to choose it satisfying some conditions, and maybe those conditions are too stringent to actually apply the Sard-Smale theorem in this way. So,
do you want it to be like invariant under the symmetries or something?
Something like you want various things of that sort, yes. I reserve the right to not talk about that anymore because other people will, and I'm going to talk about the alternative, which is in the title of my mini course, so-called classical, or what many people call geometric perturbation methods, which is the notion that if you take a generic choice of the data in the space of data, then your actual section will be transverse to the zero section, which means, of course, the zero set of your section is a smooth manifold, and finite dimensional as well, because we're in the Fredholm context. And, well, the space we're actually interested in is that divided by some kind of symmetry. That, in general, will be an orbifold. So an orbifold is something that looks locally like Euclidean space divided by a finite group action. And that's what you get if you're taking a finite dimensional manifold and dividing it by the kind of symmetry groups that we're interested in. So that is minor headache number one to be aware of. We won't get manifolds in general, but we could get orbifolds if we're lucky. Much larger headache number two is that often we're not lucky and this condition simply isn't true. And Dusa already talked about that a little bit. I'm going to talk about that some more. So that's all I will say about generalities. I'm going to focus on this classical approach over 3 talks. And in a particular context, I want to discuss symplectic field theory. So in the original propaganda paper in 2000 by Eliashberg, Giventhal, and Hofer, you have symplectic field theory presented as a very general way of defining invariance of contact manifolds and symplectic cobordisms between contact manifolds. And, well, one can do it even a little bit more generally than that, which is sort of nice for certain purposes. So I'm going to talk about stable Hamiltonian structures. So first of all, if M is an odd-dimensional manifold, a stable Hamiltonian structure H on M is going to be a pair capital omega lambda, which consists of the following. We have first omega is a closed 2 form of maximal rank. So you should imagine that as something that arises on any hypersurface in a symplectic manifold. Right? You just take the symplectic form and restrict it to a hypersurface. It's going to be a closed 2 form of maximal rank. If I omit the word stable, that's what we call just a Hamiltonian structure. Now, stable comes from this additional 1 form lambda, which satisfies following properties. First, lambda wedge the top dimensional power of omega must be a positive volume form. So this implies in particular that you can take omega and restrict it to the kernel of lambda. Lambda is nowhere 0. So its kernel is a hyperplane distribution, which I'm going to call psi, as I always do with contact structures, because that's one important example. Could be a contact structure, but in general it's just some hyperplane distribution. And omega makes that hyperplane distribution into a symplectic vector bundle. Gives us a symplectic bundle structure. Okay? And then the other condition, since omega has maximal rank on an odd dimensional manifold, it has a kernel that's always one-dimensional. Right? That's the so-called characteristic line field, the one dimension of directions in which omega is degenerate. So what I'm going to require is that d lambda also vanishes on that same kernel. Another way of saying it is that the kernel of omega is contained in kernel of d lambda. Okay, so this is a definition which has been around for several years, and as stated, it's not too hard to understand, but I think a lot of people don't really understand what it means. So let me talk a little bit about that. First observation is that if I now take this odd dimensional manifold and look at a small cylinder constructed out of it, so some small interval times m, this thing now inherits a natural symplectic form. Let's call the real coordinate little r and define little omega to be d of r lambda plus big omega. And now it's an easy exercise. That's going to be a symplectic form. As long as this cylinder is sufficiently small, it might even be symplectic for epsilon larger than that, but in general, I can only guarantee this is true for epsilon small. Moreover, what does the characteristic line field look like if you restrict? You've got a one-parameter family of hypersurfaces. Let's say m sub r is the hypersurface r times m sitting inside that cylinder. The characteristic line field of omega restricted to m sub r is independent of r. So it's the same characteristic line field for all parameters in my parameterized family of hypersurfaces. That's really the original definition, which I think appeared first in the book by Hofer and Sander of a stable hypersurface. And that's where this idea comes from. It's the kind of situation in which you would expect to be able to prove something like the Weinstein conjecture that asserts existence of closed characteristics of this characteristic line field. Because if you have them on some hypersurfaces in the vicinity, you have them on all of them.
Excuse me, what do you mean with the first symbol of the last line?
The first symbol? That's an and. Ampersand.
Okay.
So it's in order to get the stable condition that you want this last condition that the kernel of omega is contained in the kernel of d lambda. That's what implies.
That's what implies this fact about the characteristic line fields. Exactly. Right. Yeah. And conversely, if you are given a one-parameter family of hypersurfaces that has this property, this stability of the characteristic line field, then you can always find a stable Hamiltonian structure that produces that. So that's kind of an exercise using the Moser deformation trick.
How much will I lose if I just ignore this definition and pretend you said contact structure?
Nothing really. Yeah. That's a perfectly good point. If you don't like this definition for some reason because it's new, just think lambda is a contact structure and big omega equals d lambda. Okay. I was going to say that soon anyway. So there is from this data, we have also a canonical generator of the characteristic line field, which by analogy with contact forms, we'll call this the Rabe vector field. So my notation will be R sub h. And it's determined by the conditions omega annihilates the direction, of the Rabe vector field, and then we normalize it by lambda.
Is there any reason d lambda couldn't be 0?
No, there's no reason at all why d lambda couldn't be 0. No. I will also say that again in a moment. So we have a stable Hamiltonian structure. It defines this hyperplane distribution psi, which might be a context structure in certain examples, but doesn't have to be. Could also be a foliation. We have this Rabe vector field. Another thing we can do is, since we have this small symplectic cylinder we built out of it, we can also just arbitrarily expand that to r times m and rewrite my symplectic structure there in the form omega phi. That's going to be d of phi of r lambda plus omega. So what's phi? Phi is going to be in the space of smooth functions taking r to that same small epsilon interval with strictly positive derivative. So this is a symplectic form also. Okay? It's symplectomorphic to the one I wrote down before. I've just stretched things. But the point is that R cross M is the kind of setting where I would like to talk about J-holomorphic curves. And I can do that now by saying, well, the space J dependent on the stable Hamiltonian structure is going to be the space of almost complex structures J on R cross M, which I will assume always to be R invariant. In other words, there's this R translation action on R cross M. I want that to preserve all my J's. I also want to say that J maps the unit vector in the R direction to the Rabe vector field. And I want to say that J preserves my hyperplane distribution as well as the symplectic structure, and is compatible with the symplectic structure on that. So let's say J restricted to psi is omega compatible. Okay? So here's a lemma which is very easy to prove and sort of helps justify all these definitions. That is that for all choices J in this space of translation invariant almost complex structures and all functions phi, as I indicated above, that are mapping to that small interval with positive derivative, it's not just that omega phi is symplectic, but in fact it's compatible in the usual sense of Gromov with this choice of J. So I can fix J and I can then allow any choice of phi I want. And that's an important detail for defining things like the energy of a J-holomorphic curve, because we then take that to be the supremum of symplectic area defined with respect to all these different choices of symplectic forms. So let me give two examples. They've already sort of been mentioned. First of all, if alpha is a contact form, we get a stable Hamiltonian structure d alpha comma alpha. And then this symplectic manifold R cross M with this kind of symplectic structure I've been talking about. I'm not going to try to say this too precisely. You have to make some kind of condition on how you define phi in order to say this, but I'm just going to say one can do it. So this is what's called the symplectization of the contact manifold. Yeah, I really should relax the epsilons in order to say that. I should actually Should at least make plus epsilon be infinity. But let's not worry about this right now.
Can you quickly write down what the symplectization is?
No. I'm going to say it's this.
Okay.
Yes?
So what's the condition where you can integrate this hyperplane distribution to a symplectic manifold?
Where you can integrate the hyperplane distribution.
Yeah, if you integrate it and then you find a submanifold which has that as its tangent bundle.
Well, for the hyperplane distribution to be integrable, I think that's equivalent to saying that d lambda vanishes on psi. Right. So certainly it's sufficient if d lambda vanishes altogether, which is my next example.
Already in the first row, we think that the word compatible sort of looks like compact. So
Well, I'm sorry.
maybe
I'll take this opportunity to make a blanket apology for my handwriting, as I customarily do. There isn't that much I can do about it. Okay, compatible.
You just add an I, so it's like
Compati. All right, second example. If M equals the product of S1 with some other manifold W, and I take W to be a symplectic manifold. So let's say I have symplectic form little omega on W, and then set capital omega to be that plus dt wedge dh. So here t is the S1 coordinate, and I'm choosing some function h, a Hamiltonian function, which is dependent on time in a periodic way. So this is capital omega, and I take lambda to be just dt. This is a case where it's closed. D lambda vanishes entirely. So now one can check this also is a stable Hamiltonian structure. And it has a meaning which a lot of people will probably like. You can compute the Rabe vector field for this. It's the vector field in the t direction plus a vector field in the w direction, which is precisely the Hamiltonian vector field. Okay? So this is a way to turn questions about Hamiltonian vector fields on symplectic manifolds, even time-dependent ones, into questions about a time-independent Rabe-like vector field on an odd-dimensional manifold. And it gets better because for the class of almost complex structures that we've talked about, a J-holomorphic curve in R times this is basically equivalent to a solution of the Floer equation in W. So this is a way that you can do Floer homology, Hamiltonian Floer homology, from the perspective of symplectic field theory. Okay. So now the setting in which I really want to think about holomorphic curves is also a bit more general than this. So let's take a symplectic manifold. So here I'm talking about cobordisms. With stable boundary. So one can define stable boundary in various ways. The main thing I want to say is there exists near the boundary a one-parameter family of hypersurfaces that all have the same dynamics on them, same characteristic line fields. And that's equivalent to saying that there exists this collar neighborhood near M plus that looks like a small interval times M plus, where the symplectic structure is just the kind that I wrote down already, d of t lambda plus omega plus for some stable Hamiltonian structure omega plus lambda plus on m plus. Of course, I'm going to do the same thing on m minus. But the collar neighborhood will look like an opposite interval. Okay. So this is the definition of a symplectic cobordism with stable boundary. And having done that, I can add cylindrical ends to this compact object and get a non-compact object. That's what we call the completion. So I'll denote that by W hat omega hat. It's going to depend on some choice of function phi of the sort that I use to define symplectic structures on symplectizations. And that choice of phi is not particularly meaningful. It's just nice to know that I can do it. So the definition is we take a negative cylindrical end, glue that along m minus to W, glue that along m plus to positive cylindrical end. And the symplectic structure here, we take omega phi on each of the ends. And if the original omega on W, you can choose the function phi such that, so remember, I still have this definition on the board somewhere. Middle board top right. Very good. D of phi times lambda plus omega. If I choose phi so that it equals just the identity map close to 0, then I can obviously glue these cylindrical ends smoothly together with these collar neighborhoods. That's what I'm doing. Okay. So with that choice of symplectic structure, and I don't really have to specify phi, I just know that I can choose one.
Are you using the same phi on the both ends?
I don't care. Actually, I specifically want to not specify phi and allow myself the freedom to change it. So let's say J of omega and the two stable Hamiltonian structures. This is going to be the space of all almost complex structures J on the completion W hat, which I assume to be everywhere compatible with, well, let's just say compatible with omega on the original compact object and belonging to these spaces with respect to the stable Hamiltonian structures that I already defined. So the spaces of translation invariant almost complex structures on the ends. So that now is going to be an almost complex structure that's compatible with omega hat phi, no matter what phi I choose. Okay. So now to start talking about the actual J holomorphic curves. Any questions so far? Yeah.
So this, you require that J's, what does it say?
Compatible?
Translation.
Compatible. Translation variant.
Translation variant on the end. So what about like in the cobordism part? I mean, don't you have a factor of R there anyway, you know?
Well, in the cobordism part, I don't have a factor of R except close to the boundary.
Yeah. Okay.
Yeah, and I don't make any requirement there except compatible with the given symplectic form. Okay, so the kinds of holomorphic curves we're going to talk about are as follows. We take sigma j to be a closed Riemann surface. let's actually say there's going to be two finite disjoint ordered subsets. And in particular, sigma dot always denotes sigma with the first finite ordered subset removed. That's a punctured Riemann surface. And we take that, also this subset, I don't have to worry about it too often, but it gets partitioned into the so-called positive and negative punctures. Each of those could be empty, but each puncture belongs to one or the other of those. And now I think about maps from this Riemann surface with the various points removed going into my completed symplectic cobordism. And I want them to be what I call asymptotically cylindrical, which means, well, let's not write down the precise definition. Let's just say asymptotic near each positive or negative puncture z to r times a Rabe orbit in m plus minus.
Chris, you're missing a hole somewhere.
I'm missing a hole, that's true. Could be worse. The opposite would sound like a medical emergency. So what I mean is essentially, for this kind of almost complex structure I'm considering, with the translation invariant thing satisfying these conditions on the ends, right? I have J maps the vector in the r direction to the Rabe vector field, which means r times a Rabe orbit is always a holomorphic cylinder in the end. So those are special holomorphic curves that always exist, at least in that region, maybe not globally. And I want to consider punctured holomorphic curves whose behavior near each of those punctures approximates one of those cylinders better and better as you go toward the puncture. Right? So to make it precise, I would say you can choose some holomorphic cylindrical coordinates near each puncture. And in those coordinates, as you go further up toward infinity on the cylinder, your curve looks more and more like one of these trivial orbit cylinders. Okay, maybe it's time to recover this. Yeah.
In your picture, theta is empty, or what's happening?
Theta, I haven't really said. Theta doesn't have to be empty. It's just some finite subset right now.
But in the picture,
It doesn't appear in the picture because it doesn't affect the picture in any way.
Okay.
It's just points.
Okay.
Right. So theta are meant to be marked points. All right. So the actual moduli space looks like the following. It's going to be a space of tuples sigma, j, gamma, theta, u, where, well, sigma j is a closed Riemann surface as I wrote above. Gamma and theta are these disjoint ordered finite subsets, so let me not rewrite that. Mainly I need to say u maps the punctured surface to the completion w hat, j holomorphically, and asymptotically cylindrically. And then I just need to say what my equivalence relation is. Dusa basically already said it. You could deduce completely the right answer to this from what Dusa said. I will say a tuple sigma j gamma theta u is equivalent to a tuple sigma prime phi star j phi inverse of gamma, preserving the ordering, phi inverse of theta, u composed with phi for any diffeomorphism phi from sigma prime to sigma.
Presently, the ray orbits are allowed to be arbitrarily terrible.
Yeah. This definition is still okay if I allow the ray orbits to be arbitrarily terrible, but I won't have any theorems. Yeah. I do have, so finally to make some use out of the marked points, I have an evaluation map sending this moduli space to W hat M, where theta, the marked points, are labeled zeta 1 through zeta M. So this just evaluates U at those points. And it's well defined because of the way that I defined my equivalence relation. Right? These diffeomorphisms map the set of marked points to the set of marked points. All right, so let's finally state a couple of theorems. So theorem 1 says, if I have, I'm just going to abbreviate elements of this moduli space by U instead of writing out the entire tuple and saying equivalence class and everything. So if U is what I call Fredholm regular, that's a condition I'll have to explain a bit, and it also includes the condition that the asymptotic ray orbits are not arbitrarily terrible. Then a neighborhood of U in the moduli space is a smooth finite dimensional orbifold with isotropy at U isomorphic to the automorphism group of U. So I didn't write down this definition yet. The automorphism group of U is simply the space of all biholomorphic maps of its domain which fix the punctures and the marked points and satisfy U equals U composed with phi. So unless U is constant, that's always going to be a finite group. And for somewhere injective curves, it's going to be a trivial group. But for non-somewhere injective curves, so for multiply covered curves, if we get this Fredholm regularity condition, whatever it is, we're going to have to deal with an orbifold rather than a manifold because of this isotropy.
Is this theorem supposed to be essentially a tautology on the word regular?
In some sense, this is a tautology on the word regular, yeah. I mean, one does have to work a little bit to see why you can make this local identification of the moduli space with something that looks like an orbifold, even if you have regularity. And that's, I will at least have time to get to that in this talk, I think. Theorem 2, I'm going to probably postpone the proof of this for tomorrow, but I'll state it now. Let's say, let's fix an open subset U with compact closure then I'm going to say there exists a bare subset called JU reg. Well, it's a subset of the space of all. Oh, I needed to fix some more data in advance. So fix also an almost complex structure J naught of the type I've described, okay, then there exists a bare subset. So this is a subset of the space of all J's of the type I've described, with the extra condition that J matches J naught everywhere outside of this special subset U. So this special subset U we can call the perturbation domain. It's where we're going to allow ourselves to change the almost complex structure, but we leave it fixed everywhere else. So, such that for all J in this J reg U, let's finish it over here. Every somewhere injective curve U in the moduli space with respect to J, passing through my special subset capital U, is Fredholm regular.
But here, bare subset is again comeager.
Bare subset literally means co-meager, yes. So
What I call residual, or
yeah, I never understand residual. It sounds to me like it means the opposite, so I don't use the word. Some people call it second category, which I think is also not technically right if you look up the actual definition of second category. Yeah. Thank you for that input, Katrin. Yeah. Well, someday some kind of sensible general habit will prevail, hopefully. I say bare subset, and most people don't seem to mind. So the literal meaning is countable intersection of open and dense sets.
or it contains, actually, if you're being strict, it contains it.
Contains a countable intersection of open dense sets. Very good.
Maybe more useful input is though somehow I think you're assuming here now that the Hamiltonian structure is sort of regular, right?
Well, that's in theorem 2. I am. That's true. Thank you. Okay. So the board's out of reach, so I'm not going to write it. Let's just say this. The one additional condition you need in theorem 2 is that let's say all the closed Rabe orbits for both stable Hamiltonian structures are non-degenerate. So under those conditions, theorem 2 holds. Otherwise, you could have trouble. And at least for if your stable Hamiltonian structures are contact forms, that's a condition which is generic. That's a standard result.
Can you also do this if your Rabe orbits are more spot?
More spot is also fine, yeah. More spot or non-degenerate are perfectly fine. Okay. So let's talk a little about the functional analytics setup for a neighborhood of, let's say I have a specific element of the moduli space with complex structure J naught, and the map is called U naught.
Just to understand the statement of theorem 2.
Yeah.
You're not asking that it be somewhere injective inside U. It has to be somewhere injective somewhere and pass through U.
Those two things are equivalent, which is a not so hard theorem. So what I really should ask for is that there is an injective point mapped into U. Okay, and it's a good point because if I were working in other settings where I have boundary with Lagrangian boundary conditions or something, then it's not necessarily true that just because the curve is somewhere injective, that its injective points are dense. So then I would have to be careful. But here, injective points are dense if the curve is somewhere injective. Yeah.
I think you've hidden the end of the statement. Can you
rise the board, which is here.
Ah.
The statement is on the sideboard.
Oh, it's this one.
It goes from.
It's this one.
Maybe you could claw up that board so it's up with the your own.
This is called democratic blackboard technique. All right. So I need to actually write down some kind of Banach manifold of maps that will contain the solutions I'm interested in. This is something that's kind of standard in the case of closed maps from closed Riemann surfaces, and for punctured curves, I guess it's considered sufficiently standard that nobody really feels they need to go through the details when they write papers. But it means there is no paper where anyone does the details, really, as far as I think. In Matthias Schwarz's thesis, I think there may be details about this, and that's possibly the only place.
There's also this paper by Drogomir Dragnev. He
No.
kind of gives it.
No. Well, I mean, what he does in there is basically just lifted from Schwarz's thesis. So, yeah. Okay, so I'm going to talk about a space of Sobolev class maps from the punctured surface to W hat, class WKP. So I want to have k derivatives that are of class LP locally. Locally, that would be the definition, and it's not hard to express, but globally, what does this mean? Easiest way to say is U is of the form exp along f of h, where f is going to be some smooth map which is not just asymptotically but literally cylindrical near the ends. I'll say that in a moment. H is going to be some section of class WKP locally along the pulled back, so of the pulled back tangent bundle along F. So in compact subsets, this is a sufficient definition, but I need to say more specifically what happens at the ends. So yeah.
So I missed that conversation. So the J0 that you started with is regular, right? Was that?
No, I don't care. It doesn't need to be regular.
So are we requiring anything for J0 to begin with?
I don't have to require really anything about J0 because I'm going to perturb it in a certain region, and I'm only looking at holomorphic curves that pass through that region. Yeah. So near each puncture in holomorphic cylindrical coordinates, I can choose coordinates st, which are in a half cylinder. I'm going to call it a positive half cylinder if it's a positive puncture, a negative half cylinder if it's a negative puncture. And then the requirements are that the map F just looks like Ts plus a constant gamma of Tt plus a constant in the cylindrical end r plus minus times m plus minus. So here C1 and C2 are just some real constants. And
what do you mean by gamma plus a constant?
I'm about to say that. Oh, sorry. Well, the gamma will be valued in S1. You can add constants in S1.
I thought gamma is an M.
C2 is inside the.
Very good point. Is that better? Thank you for that. So gamma is going to be a t-periodic orbit of the Rabe vector field. And then what I say about H is simply that in these cylindrical coordinates, where also I'm assuming I've chosen some kind of sensible asymptotically translation invariant trivialization of this tangent bundle, I want to have H on that end be of class WKP on the cylinder, the half cylinder. Okay. And so I haven't said anything about what K and P are. I'm not really going to make any requirement about that, except K times P should be greater than 2, because then the Sobolev embedding theorem tells me WKP injects continuously into C0. So these maps are at least always going to be continuous. If they weren't continuous, I'd have real troubles making this a good definition.
So you don't require any kind of exponential decay for H or anything? Just
I'm getting to that. I'm getting to that.
Chris, so I'm confused because if we're looking at a neighborhood of U naught, shouldn't we be writing things in that neighborhood in the form X sub U naught of something?
Yeah, but I'm going to, well, U naught is going to be a map of this form, and I'm going to consider other maps of this form that are close to U naught. I'm still, I mean, I haven't localized yet. This is still global at this stage.
And you also not yet closed your set.
Yeah, the bracket's still open.
Oh, very good. Wouldn't want to have some sort of general LaTeX error.
Can you explain what's being ruled out by this list of conditions?
Well, I'm ruling out maps that don't have decay at infinity to some very sort of, well, F is a very controlled map. It has this precise cylindrical form. I'm only considering maps that have asymptotic decay to a map of that form. So I don't want them to move around non-trivial amounts arbitrarily far away. All right. Augustine kind of preempted the next little variation I have to put on this. And I won't be able to explain why just yet, but let's just say it. For a parameter delta, I can let, I'm going to call this B. This is the actual Banach manifold that I'll work with. So this is going to be, again, U equals X belong F of H as above. But the condition on H will be slightly different. I'm going to require that the norm of H, not the norm of H itself, but the norm on the half cylinder of e to the delta S times H is finite. So that enforces some exponential decay, in addition to the decay that the WKP norm already requires. So I'm not going to tell you yet why this is necessary. I will tell you that eventually. I will tell you why it's possible, which is, call this fact, though I guess it's sort of a hard theorem. First version of it proved by Hofer, Vysotsky, and Sander. And there have been other versions in various contexts since then, that if the asymptotic orbits are non-degenerate, then for all delta sufficiently small, all asymptotically cylindrical or let's just say all curves in the moduli space I've defined belong to this Banach manifold. That is, the map involved in defining that curve belongs to that manifold. It has the asymptotic exponential decay, as long as delta is sufficiently small.
Hey Chris, I'm in the back row. I can't quite see. Are there absolute value signs around that s in the exponential?
No, but there should be. Thank you. Let's make it a plus or minus. Right? I want a minus sign if I'm at a negative puncture. The point is that it enforces asymptotic decay or exponential decay rather than exponential growth or something. Now, what can I sensibly say in the 0 amount of time I have left?
You have like 3 minutes.
My question stands. That would be remarkable.
So in that last HWZ theorem, the delta doesn't depend on the component of M of J you're in.
Yeah, it does. Yeah. To say this properly, I would have to say that given a specific set of asymptotic orbits, there is a delta sufficiently small so that all curves that are asymptotic to those orbits satisfy the decay condition. Okay. So let me try and at least get to the definition of Fredholm regularity in some form. So what I'm going to do now, I've defined a class of maps I want to work with. I also have to worry about the complex structure and the domain, because that's not fixed. It's not some sort of God-given data to work with, but I allow it to vary, and different points in this moduli space have different complex structures. Now, I'm looking at just a neighborhood of some U0 with complex structure J0, which is it still visible somewhere on the board? No. There it is. So let's just worry about the complex structures that are close to J0. And one way to do that, I don't have to consider everything in this infinite dimensional space of complex structures. But if I want to cover all of them that are not equivalent by diffeomorphisms, I can think about Teichmüller space. That's at least a nice smooth manifold. So what I'm going to do is say let T be a smooth finite dimensional family of complex structures on sigma, which I can, if I want to, I can even assume that they are fixed near gamma and theta. Another thing, right, I can just take a model surface sigma and fix punctures in one particular place, or several particular places, fix also the marked points in particular places. I don't need to allow them to move around, because if I want to get all the different conformal structures up to equivalence with these punctures and marked points, all of them can be represented by some complex structure that have the punctures and the marked points in that particular place. Right? That's just a question of choosing a diffeomorphism. So I'm fixing gamma and theta in place on sigma, but I'm letting the complex structures vary. And this is going to be a smooth finite dimensional family that parametrizes a neighborhood of the equivalence class of J0 in Teichmüller space. What's that?
I don't understand what you just said. Suppose that these like W, how do you say, the ends are empty and sigma is the sphere.
Yes.
Then you're not varying the complex structure at all. Because you can, but you're saying that you can get any configuration of points that you want.
Yes, I can. But I have to vary the complex structure.
You could, because the complex structure is just a section of the tangent bundle. I mean, automorphisms of the tangent bundle, they're all diffeomorphic.
I see.
But you can certainly vary them.
And they're not all diffeomorphic if there are more than 3 marked points.
No,
so okay. Even on the sphere, I have to do this sometimes. Okay. So I'm parameterizing a neighborhood in Teichmüller space, which is the space T sigma dot of theta of all complex structures on sigma divided by the identity component of the diffeomorphism group preserving or fixing punctures and marked points. Okay? So it's a classical fact that this is a finite dimensional manifold. So I can choose some sort of finite dimensional space of complex structures, parameterizing it. And there are various sensible ways to do this. We'll talk about tomorrow if I have time. There's a quick lemma. Let's also assume, just for simplicity at the moment, that the Euler characteristic of the punctured surface minus the marked points is negative. Dusa also talked about this a little bit. That's the stable situation. So that's the situation in which the automorphism group of the domain with its punctures and marked points is finite. It's not an absolutely necessary assumption for what I'm talking about, but it does make a few things easier. So I can, in particular, say there exists a choice of this object T. I'm going to, in the future, call this a Teichmüller slice, since it parameterizes a neighborhood in Teichmüller space that is invariant under the action of the automorphism group of the domain. Okay. So having made this choice, let me finally write down the point of theorem 1. We now can define a smooth section of some Banach space bundle the domain is going to be the product of the Teichmüller slice with my Banach manifold of maps. The section is called d bar j. So the fiber over j comma u is going to be the space of wk minus 1p sections of the bundle of complex antilinear maps from T sigma j to pulled back tangent bundle. I hope that's the right number of parentheses. If not, somebody will surely let me know. And we're going to take j comma u to the obvious thing, tu plus big J composed with tu composed with little j. If you tell me I need to put a 1/2 in there somewhere, I will tell you to get a life. And so finally,
how about changing the T for a D?
My own PhD students need to be especially careful in moments like that. So
Analyst's notation using T.
I go back and forth. So the lemma is that the automorphism group of U acts on the zero set of this section by, well, the obvious phi star j U composed with phi, such that a neighborhood of U in the moduli space is in bijective correspondence with a neighborhood of the equivalence class. So I should have said neighborhood of U naught in the moduli space with the equivalence class, this automorphism group of U naught, J naught U naught in the zero set modulo that action by the automorphism group. So now, what does this really say? By the implicit function theorem, Mj is going to be an orbifold near U naught with isotropy group equal to the automorphism group if that zero section is a manifold, which is going to be true if the linearization of the section is surjective. So that's some linear operator from the direct sum of a finite dimensional space tangent to a space of complex structures with, well, let's just write it as tangent space to the Banach manifold, which is some space of sections of the pulled back tangent bundle of class WKP. Yes. Sorry?
There should be a delta on your E, in the definition of E.
Oh, you're right. Thank you very much.
Flo told me he wants to have a live, it's lunch now.
This is the moment where I say I thought you people cared about mathematics.
I already said
Okay, basically, I wanted to at least end with having written down this operator, right? So Fredholm regularity means, specifically, I need to finish the sentence and say is surjective. Okay, so Fredholm regularity means just that. This operator is surjective. I'll talk more tomorrow about what one needs to do to make sure that that operator is surjective. The result is then we identify local neighborhoods in the moduli space with this thing, which is a finite dimensional manifold divided by a finite group. Okay? I'm not going to say anything about the proof of the lemma, except that if you stare at it long enough, it becomes obvious. It's not that hard. Okay, so I'll stop there for now.
So there is office hours, so I again suggest longer questions get postponed until then. Does anyone have a short question that they're willing to ask before lunch?
So in practice, I mean, you want to show that something is regular, right? I mean, what do you need to put it, take in the slice and vary your complex structure in the...
Right. Okay, and it's a good question. If you want to show that something is regular, well, the answer is I've never been in a situation where I had to actually choose a Teichmüller slice concretely. But it has to be there in the theoretical setup, because if it's not there, right? I mean, it would obviously be sufficient if the linearization of this operator just mapping this space of sections to this space of sections is surjective. That would suffice. That would imply that this one is surjective. The problem is that that's not true as often as you want it to be. Right? You have this additional finite dimensional stuff in the domain, which sometimes actually makes the difference between an operator with a finite dimensional co-kernel and one that's surjective. So in fact, so if I have time to talk about automatic transversality tomorrow, hopefully, it's a really crucial detail there. The criterion that you use to prove automatic transversality does not work if you leave out this whole discussion of Teichmüller space, because you need to have this freedom to vary the complex structure in order to get as much transversality as you need.
Do you have an actual example of a curve which is regular in this sense and not regular if I take this slice?
I could probably come up with that. Ask me in office hours.
And you have a discussion tomorrow.
And I have a discussion tomorrow.
In addition to your lecture.
Yeah, you can certainly find examples if you take tori on surface of higher genus, where you definitely need to vary the Teichmüller space to get
What is the fact that you take a finite dimensional family and it's just all by you?
If I took all of them, this operator would not be Fredholm. That would be bad.
So here you're thinking of fixing big J, which is the complex structure on the target.
So far I'm fixing big J.
And your space of J here, I was using a curly J to mean variations of J on the target space, but you're fixing that and making your J as a finite dimension.
Well, I have two curly J's.
Well, you have two curly J's, but only one on this board. You see, your curly J there is a Teichmüller slice.
Yeah.
But you could, in principle, vary the other J on the target space if you wanted to.
Yes. You mean finite? You mean talking about finite dimensional families, or you just generic?
I mean, in your theorem 1, you were saying that you were taking generic elements where you were allowed to vary in the target of an open subset U of your target, right?
Mm-hmm. Yeah,
and that curly J is not actually in this lemma. Here you're somehow assuming you fix that.
Right. No, I mean, the question of why you get transversality for simple curves for generic J I will address tomorrow. So far, all I've talked about is what criterion actually gives you smoothness of the moduli space, and how does one go about proving that.
Yeah, one thing to say is why you need to vary J in Teichmüller spaces. For example, if you look at the space of tori in CP2, and look at, so you know there are curves of degree 3 embedded tori. You look at the induced complex structure on the torus, that changes. So if you fix the complex structure on the torus, it's not necessarily going to be regular, because when you move your point around and you move the curve around, J on the domain naturally changes. So you have to have that variation in.
Without further ado, I propose we break for lunch, and at 2 p.m. I'll make some short remarks about organizational things like finances and stuff, so I'll see you at 2.
At the end last time, I left myself the task of proving a theorem that you can achieve transversality for symplectic, for holomorphic curves in symplectic cobordisms for generic J. Let me repeat the statement quickly. So the setting is the completion of a symplectic cobordism, which has stable Hamiltonian structures at the positive and negative ends. And I've fixed some open subset, which I said is precompact, so it's an open and bounded subset. And let me introduce some new notation slightly better than what I did last time. Let's say J fix is just some choice of almost complex structures, some choice of almost complex structure in this special class I defined, compatible with the symplectic form and with the stable Hamiltonian structures. And now the statement of theorem 2 says that there exists, I guess I'll say the word co-meager since everyone else is, a co-meager subset JU reg sitting in the space of all almost complex structures compatible with the data which also match our choice J fix outside of this subset U, such that all well, let's say for all j in this special class, all holomorphic curves in the moduli space defined by j with injective points in the subset U are regular. Okay, so somebody asked the question last time whether I really need to say that the curve is not a multiple cover or somewhere injective, or just that there exists an injective point in the perturbation domain U. The answer is all those things are equivalent in this situation, but I'm stating it this way because in the proof that's precisely what we need. We need the existence of an injective point that gets mapped into the perturbation domain. So in other situations where those conditions are not all equivalent, still this is what you need. All right, so I've got a few choices of the technicalities when I go about something like this. I first need to decide in what space exactly of almost complex structures do I want to consider perturbations. And well, there's a natural space in the picture, which is the wrong one, because what I'm really interested in, of course, is this space of almost complex structures that I assume are all smooth, with the C infinity topology on it. And you can call that a Frechet manifold, at least, because I'm saying M when I mean W hat, apologies. So W hat, of course, is not compact, and it's not so easy to define either Banach norms or even semi-norms on a non-compact domain, but of course, I'm only allowing these perturbations to be non-trivial outside of this compact subset, or inside this compact subset. So it's easy enough to define semi-norms, and I can call this object here a Frechet manifold. But Frechet manifolds are not very useful to me, because the implicit function theorem doesn't hold, the Sard-Smale theorem doesn't hold. There's a whole lot of analytical results I need, which I can't use. So really, I need some Banach manifold.
What do you mean by with injective points in U precisely?
Sorry?
What do you mean by with injective points in U?
So injective point is, right, you understand that part, or, right. So I mean an injective point whose image is contained in the subset U.
So those exist.
That's the assumption. I mean, I'm not saying all curves have that property. I'm saying I'm only considering curves that have that property. Okay. So when you apply this theorem, of course, it's going to miss some curves, right? The typical way you'd apply it is you'd let U be the compact part of the cobordism, not including the cylindrical ends. And then it doesn't say anything about curves that are contained entirely in the cylindrical ends. But we'll have another theorem for that in a little bit. So I have to make a choice of some Banach manifold of almost complex structures. And Duza explained one possible choice yesterday, which is instead of looking at smooth almost complex structures, ask them to be of class CK for some finite k. That's a good choice, but I'm a little bit allergic to it myself, just because if I then write down the nonlinear Cauchy-Riemann operator for a J which is not smooth, then the operator on the section of the Banach space bundle will also not be smooth. It will have finitely many derivatives. The Sard-Smale theorem requires my maps to have at least some number of derivatives. I'd have to look it up to find out how many. And these are details I don't really want to worry about if I have a choice. I'd rather have everything in the picture be smooth, except for, of course, the maps themselves are going to be of Sobolev class. But I'd like J to be smooth so that my nonlinear Fredholm section is smooth. So I'm going to adopt Fleur's solution to that problem, which is to define the following object. So proof. Let's fix another almost complex structure that I will call the reference J, Jref. That's in this space as well, and matching J fix outside of U. And I'm just going to consider for the moment almost complex structures that are perturbations of J ref in some precise sense. So the other piece of data I need to fix is a set of positive numbers, which I'll denote collectively by epsilon. It's a sequence and the sequence is converging to 0. And then define J epsilon to be the space of all J's of the form exp along J ref of some y. So I'm taking exp, imagine exp to be the exponential map on the manifold of complex structures on each tangent space. That's something you can define however you like. It is a manifold, so that's fine. Y I can consider to be in the tangent space to that Frechet manifold and also vanishing outside of U. So literally this just means it's a smooth section of the bundle whose fibers are the tangent spaces to the manifolds of complex structures on the tangent spaces. And I'm saying a smooth section, but I'm also going to require that it's finite in this so-called Fleur C epsilon norm. That's defined as the sum from 0 to infinity of epsilon m times the Cm norm. So I want that to be finite. In fact, I'm going to require that it's small for some constant C. Okay. So there's an exercise one needs to do, and it's a standard lemma that you can find in various places, originally in some of Fleur's original papers, that if you choose this sequence of epsilons converging to 0 fast enough, then this norm not only defines a Banach space, but it defines one which is large enough to contain smooth bump functions supported in arbitrarily small neighborhoods of points. That's the key thing we need to know about this. So that defines a Banach space of y's, and just exponentiating that from J ref, we get a Banach manifold of j's. It's trivially a Banach manifold. I've just defined one chart on this Banach manifold. So it's a small one. And this is, in some sense, not any kind of global construction. I cannot get anywhere near a dense set of j's with this. But I can get j's at least arbitrarily close to J ref. And J ref, to start with, was arbitrary. Okay. So now, the universal moduli space, m star of J epsilon, is going to be the set of pairs U and J, where J belongs to the J epsilon space, and U is a holomorphic curve for J. And also, I want it to satisfy the extra conditions that U is somewhere injective, or namely, U has an injective point mapped to the perturbation domain U. Okay? So that's traditionally called the universal moduli space. I think given the way we're doing it, it's not a terribly good name, because it is not universal in the sense of being able to consider all possible J's that we might be interested in. We're only looking at J's that are in some neighborhood of J ref, and in fact, it's not just a smooth neighborhood, it's a neighborhood of J ref in a very peculiar topology on the space of smooth functions. Okay? At the end of the day, I'm just going to care about the fact that I can get arbitrarily C infinity close to J ref by objects in this space.
Give me a rough idea. What is this? This J, Y is roughly a complex structure, right? Or a tangent space of complex structures. What's it?
Tangent space of complex structures. So literally, it's a section of the endomorphism bundle which anti-commutes with J.
Okay. And how do you test how big it is?
How big?
What does it mean, the norm, the CM norm?
Well, pick a Riemannian metric and measure it.
Integrated.
Yeah. No, not integrate, just the sup norm.
Oh,
Okay. So important detail there is, of course, the thing is only non-trivial in this compact subset.
Oh, true, makes some sense.
Yeah. Okay. Any other questions?
So this is a different topology on the space of functions for all epsilons.
Presumably, yes. Yeah.
And how am I supposed to think about this topology? Am I not supposed to think about this topology?
Yeah, that's a difficult question. I also would not say that I really know how to think about this topology. The main things we need to know are, again, the space is large enough to contain bump functions with small support. That's a non-obvious lemma, but has a pretty quick proof due to Fleur. Otherwise, you just need to know that this space includes continuously into C infinity with the ordinary C infinity topology.
Yeah, just to make sure I understand. So if I weren't so picky about only considering C infinity J's, then I could just work with CKJs in the usual.
You could.
Yeah.
Yeah. Working with CKJs is also a perfectly fine way to do this. Yes?
I have just a question with the notation. So like about the epsilon, it means that you have like the limit of epsilons like with k going to infinity is 0, or
yes.
Okay.
Yes.
Do we also need to bound the J's we include in J epsilon to ensure omega compatibility, or is that taken care of by?
Yeah. So omega compatibility is implicit here when I said that y belongs to the tangent space of this space. Okay. So yeah, that's a linear algebraic condition on y pointwise. Yes.
Why did we have to choose the JRF? I mean, we had JFix, and then.
Right. The reason I didn't just use JFix here is that if I did, what I will have proved in the end is that a small perturbation of JFix achieves transversality. I would like to actually know that given any J in my admissible set, I can perturb that one to achieve transversality. So JRef is arbitrary, except for the conditions I stated. Okay. So hopefully we're all on the same page. Now, we have this functional analytics setup that we introduced last time. We know how to understand the moduli space of holomorphic curves locally as the zero set of a Cauchy-Riemann operator, possibly divided by some symmetry action. Let's just write that down in this case. So the result comparable to what I ended with last time is we can say a neighborhood of the element, let's say U naught is the J holomorphic curve with complex structure J naught, and the target almost complex structure is called capital J naught. So that defines an element of the universal moduli space. And a neighborhood of that element is now going to be in bijective correspondence with a neighborhood of the equivalence class neighborhood of little j naught, u naught, capital J naught in some zero set of a section divided by the automorphisms of u naught, where this section I'm talking about maps. So again, I have my Teichmüller slice. It's a finite dimensional space manifold of complex structures on the domain, parametrizing a neighborhood in Teichmüller space. B is my Banach manifold of maps of some Sobolev class from sigma dot into W hat. And then I have J epsilon. That's the one element that I didn't have in this picture before, mapping to some Banach space bundle. You can infer from this picture what the fibers of this Banach space bundle are supposed to be. I'm just going to write down the map, of course, sends little j u big J to tu plus big J of tu of little j. Okay? So that, again, is a smooth section of some Banach space bundle. It is smooth because all the capital J's are smooth. If the capital J's were not smooth, then I would have a bit more of a headache to figure out exactly how differentiable this section is. That's why I introduced the C epsilon space.
On the right-hand side, what are the parentheses?
The parentheses.
As in, what do you divide by odd? You divide the neighborhood by odd, or you divide by odd and then take the neighborhood?
I divide the zero set of this section by odd. Right? So this is some diffeomorphisms of the domain which act on all three of these. Well, it doesn't do anything to big J, but it acts on these two. The same way that we had yesterday. So, I mean, I can eliminate that from the picture here because actually U naught is somewhere injective. So I can get rid of the automorphism group. It's trivial. Okay. So I'm in the world of manifolds at this point if I'm talking about simple cos. Yeah?
So the neighborhood on the right-hand side includes a little variation in the little j naught, right?
Yes.
So does that mean that M star includes varying the complex structure?
Sure. Absolutely. I mean, right, M star is, so this is just shorthand notation. It's not just a map U, it's an element of this moduli space, which includes the data of the domain. So the domain complex structure is absolutely allowed to vary throughout this picture. Okay. So there's my section. And of course, I would like to know whether the universal moduli space is smooth. It's going to be a smooth Banach manifold if the linearization of that section is always surjective. And that's the main thing one has to prove in any argument of this sort. And we already heard a little bit from Dusa about this yesterday on why you have to prove it and why it goes wrong sometimes, specifically if you don't have the existence of an injective point. So let's talk about that. Let's write down the linearization first. It's going to take a triple y eta capital Y to, well, differentiating that thing with respect to lowercase j gives us j of tu of y. Differentiating with respect to u gives us the usual Cauchy-Riemann, linearized Cauchy-Riemann operator associated to u, which I'm just going to denote by du of eta. And then we additionally have differentiation with respect to capital J gives y of tu of j. So note, the first two terms in this expression together are precisely the operator that I wanted to be surjective when I talked about regularity yesterday. So these two form a surjective operator if and only if U is Fredholm regular. That was the definition, which I didn't really write down, but I implied it. And I have this additional term, the advantage of which is that Y is now varying in an infinite dimensional vector space. So it makes it a lot more plausible that you could force this operator to be always surjective. So how do we see if it is? That's the claim. This thing is surjective. And let me be a little bit more specific about my functional analytics setting at this point. So last time, I said that the maps U are in some Banach manifold of maps that are of class WKP, and I didn't specify K and P except to say that K times P is greater than 2, so that Sobolev embedding tells you this is contained in C0. For convenience right now, just to make my life easier, I'm going to assume K equals 1. So let's say this operator is really going to take the tangent space to Teichmüller slice plus some space of W1P class sections of U star TW plus the tangent space to big J. going to take those to sections of class LP. I need the exponential weights, as Helmut would point out to me if I don't say it myself. Okay. The subject of why I need the exponential weights should be discussed, but I don't have time for it in this talk, so I would be happy to do that in the discussion session.
Yes. What is an exponential weight?
So remember the definition of this space, right? We had this asymptotic condition on the behavior of sections that said it's not just that they are of class WKP on the cylinder, but e to the delta s times the section is of class WKP. So it forces exponential decay. The delta itself is just some small positive number. We said, as long as it's small enough, you're not losing any holomorphic curves by imposing this condition. So I'm very fond of the philosophy, by the way, that nothing you do in this whole story should ever really depend on your choice of Sobolev space, as long as you satisfy the condition for inclusion to C0 or even some larger differentiability if you want. So I don't like making this choice, but it's only the first step in the proof. If you want to then prove that the same thing is true for WKP to WK minus 1P, that becomes easy if you can prove it inductively, basically. So I'm just going to do this case. Now, so if it's not surjective, then we can say there exists some element of the dual of LP delta here that annihilates the whole image. Right. So the image is killed by some non-zero element I'll call theta in the dual of LPW. Quick digression. I don't really like this distinction people like to make between analysts and topologists and whatever else people want to call themselves. Partly because I don't personally feel like I am either an analyst or a topologist. I have no idea what I am. But enough people think of me as an analyst, I guess, that they often ask me the following question. Why do you need to worry about Sobolev spaces in particular in this whole picture, right? Why can't you just say, let's consider maps of class CK? Doesn't that give you a reasonable Banach manifold? It does give you a reasonable Banach manifold. Of course, reason number one why we might prefer the Sobolev spaces is that we have certain standard estimates for Cauchy-Riemann operators that work in Sobolev spaces, and this is what tells you that the linearized operator is Fredholm. Okay. Those estimates also do exist, for instance, in Hölder spaces. So you can not talk about CK, but CK alpha for some positive alpha. I don't know how to prove the estimates there, but they do exist. You get the Fredholm property, so why don't you use that? Isn't that still somehow simpler than Sobolev spaces? Well, the answer to that is what I'm about to do. Of course, we know what the dual space of LP is in a very concrete way. And that's not true for Hölder spaces. I mean, the answer is known, but it's not pleasant, right? The dual of LP is a perfectly pleasant object. I can write it down concretely. So this is the step where it really pays off. And actually, even I'm aware of one of the mid-90s papers by Hofer, Wysotsky, and Sander where they do use Hölder spaces for most of the way. And precisely at this step, they switch to Sobolev spaces. Okay. So I've got this element of the dual. Now, the dual is just LQ with exponential weight minus delta for 1 over Q plus 1 over P equals 1. And saying that that annihilates everything in the image means, well, I can write that as 3 separate conditions, in fact, depending on whether I operate with this thing on any of the 3 variables. So it means, first of all, that if I take any j of tu of y and integrate that against theta, which I can abbreviate as an L2 pairing. So that's the pairing of LP with LQ. That's going to be 0 for all y. Same thing will be true for operating with, so du eta. That's going to be 0. And, whoops, y of tu of j paired with theta will also be 0. So again, this for all eta, this for all y. So that's what comes of saying that theta annihilates the image. Now, the second condition in particular, you can interpret that as saying that theta is a weak solution of another Cauchy-Riemann equation, namely for the formal adjoint of du. Right? You can replace du on the right-hand side with its formal adjoint, and if that paired with all etas is 0, that means that the formal adjoint annihilates theta. Now there's various regularity results that tell you anything annihilated by a Cauchy-Riemann operator, even if it's just a weak solution of class LQ, is going to be smooth. And even better, solutions of Cauchy-Riemann equations, if they have zeros anywhere, those zeros are isolated, unless the whole thing is trivial. That's the similarity principle. So the second equation really says formal adjoint du star of theta equals 0. So by regularity, theta is C infinity and has only isolated zeros.
I mean, you first need to show that the adjoint is conjugate to some Cauchy-Riemann type operator.
Yeah, absolutely. So in the background of this is a very general fact that for any Cauchy-Riemann type operator, there is a formal adjoint which is conjugate to a Cauchy-Riemann type operator. Yeah. Okay. Now what about this second thing? Well, remember y is living in an infinite dimensional space, which is large enough to contain bump functions with small support. So I can exploit that fact and say, let's choose an injective point whose image is contained in the perturbation domain. And now I can choose y to be something that is non-zero only on a neighborhood of that point inside the perturbation domain. But I can make fairly arbitrary choices of that in that small neighborhood. In particular, I can choose y to be supported near u of z such that pointwise this pairing is positive, but it vanishes everywhere else. And that's my contradiction. Right? Because I'm able to do this because I know, in fact, I should have also added this. Without loss of generality, by moving this point, this injective point a little bit, I can also assume theta of z is not 0. Right? Because they're only isolated zeros of theta. That's what I got from condition 2.
Sorry, so is one injective point enough, or do we have kind of...
One injective point implies a neighborhood consisting of injective points. It's an open condition. So having that just in a small neighborhood is certainly enough. Yes?
Chris, is that because you can always find a y which takes a non-zero vector to another one? Is that what's going on?
I mean, yes, it is that you can find y's taking any non-zero vector to any other non-zero vector. It's a slightly non-obvious fact, given that I want y to be also tangent to the space of compatible complex structures. So again, there's a linear algebra lemma that needs to be proved.
There's a proof in our book, that I do know.
There is a proof. there's a proof in my lecture notes as well, which is copied from her book, basically, because it's one of these proofs that one can write it down very short and still get no insight from it. I don't know why it's true, but it's true.
It's a crazy formula, right?
Yes, it's a crazy formula.
So you don't use condition 1?
Excellent question. Actually, I was expecting Augustine to ask that question. I didn't use condition 1 in this proof, okay? Which kind of suggests that I didn't use the Teichmüller slice at all. That's where condition 1 came from. That's the small y, tangent to the Teichmüller slice, okay? But this does not mean that the Teichmüller slice isn't somehow important. I was able to achieve transversality here, well, for the universal moduli space without worrying about that. On the other hand, it's still true that there exist J-holomorphic curves which are stable, which have positive index, so they exist for generic big J, but not for generic little j. They will only exist for certain choices of little j, and you have to allow that j to be arbitrary in order to find those curves, right? Because if you fix the conformal structure of the domain, you get a problem that may have negative index, and those things will then not exist. So that's really, it's not so much a transversality question, but it's an index question. My second remark is I will have occasion to use condition 1 in some form later in this talk, if I get there. Yeah?
Just to check I understand. So you get from this the J regular, which is co-meter in the Floer topology.
Yeah, okay, I'm not done. Let me get there. So I proved the universal moduli space is smooth.
And why was it so important that we knew the dual in this proof?
Well, I could write down the dual as some kind of section of a bundle. It's a very concrete thing instead of an element of the abstract dual space of some other space of sections, right? And then I used this L2 pairing. Really, the crux of the argument involves this L2 pairing of sections. And that depends on having a precise picture of what the dual of that target space is. Okay? Because in the end, it wasn't, the argument I made was pointwise. It was not some abstract Hilbert space inner product or something. It was a pointwise argument at the end. All right, this thing is a Banach manifold. Now we look at the projection of that to J epsilon, taking the pair uj to just J. And the Sard-Smale theorem tells me that some generalized sense of almost every j will be regular values. So there exists a co-meager subset, let's call it J epsilon reg in J epsilon, such that for all J and J epsilon reg, and uj belonging to this universal moduli space, so in particular, u has an injective point in the perturbation domain, then u is regular. And in particular, the moduli space with respect to J itself is a smooth manifold. So that's great. A corollary of that is that the set of regular J's in this larger space of smooth, almost complex structures that match J fix outside of U is dense. That's immediate because I've achieved regularity for J's in J epsilon, which are arbitrarily C infinity close to J ref, and J ref was arbitrary. That's why I chose JRef instead of JFix. So now this is good. I have density of the regular almost complex structures. I think Katrin would tell me I should be satisfied, but I'm not.
She's not here.
So
I have a quick question.
Yes.
So you're using Sartre-Smale. Well, do you need some sort of Fredholm condition?
yeah, so Sartre-Smale depends on the fact that indeed this map here is this projection is Fredholm. That's equivalent to the fact that the Cauchy-Riemann operator is Fredholm.
Yeah.
That's an easy exercise. Yeah. Right. So I disagree with Katrin's philosophy in a certain sense that, first of all, it's definitely not true that I should always be satisfied to get a non-empty set of regular complex structures. Maybe that's good enough if I only care about defining a theory that I want to prove is an invariant. But if I then also want to compute that theory, I need something more, right? Because usually I can make some specific choice of J for which I am able to count all the holomorphic curves I care about. And of course, that J is not going to be generic, so I need to make a generic perturbation of it. And I need to be assured that I can do such a perturbation of that specific J where I understand everything and obtain something regular. So density is at least what I need. I would like a little bit more, in fact, because it's often true that I want to take some space of almost complex structures that I've proven are regular in a certain sense, and now intersect it with another space that's regular by a slightly, with different conditions. Okay? Sometimes I want to do some countable intersection of those. Well, even an intersection of two dense subsets can be empty. So I'd actually like to know that I get co-meager, so countable intersection of open dense subsets. Now, how do I get from here to there? There's a trick for this that was introduced, as far as I know, by Taubes. And it also appears in the book by Dusa and Dietmar, using it for different purposes, because they've got finitely differentiable, almost complex structures. Instead, I'm trying to get now from C epsilon to C infinity. You can apply it in more or less the same way. I think people often don't realize just how widely applicable this is. And I'm going to do a kind of lazy version of it based on the fact that we know the space of holomorphic curves has a nice compactification. Okay? One can be less lazy and formulate conditions that are in some sense equivalent to that, but requiring less knowledge. I'm just going to say the following. Let's let M good of J denote the space of all curves U in the moduli space which have an injective point in the perturbation domain. And now for each natural number n, define a subset of the whole moduli space, Mn of J, to be the space of all curves with the property that the distance in some metric that I'm not going to specify, but I know where to look up a proof that it exists, distance from U to the complement of the good space in the compactified moduli space. So compactified moduli space minus M good. I want that distance to be greater than or equal to 1 over n. Okay? So in order, one can make this precise. To do it, one has to look at the appendix of the SFT compactness paper, where they prove that the topology defined on the SFT compactification has a metric. So distance with respect to that metric. So this obviously is a subset of M good. If I take arbitrarily n, large n, I can exhaust M good with this countable union of these subsets. But also this subset is compact. It's a closed subset of a compact metric space. And it's even compact in a slightly stronger sense because this metric on the compactified moduli space depends continuously on J. So I can also move J around. And if a sequence of J's converges, I can also get convergent subsequences of objects in this sequence of spaces. So the consequence of that, yeah.
The space and n, the U must come from space and go.
Yes. Yes.
Which you have now.
It follows from the definition, yeah. Yeah, because the distance is from there is positive. So let's define J reg n to be simply the space of all J's in my admissible class such that all curves U in Mn with respect to J are regular. So that's some set of almost complex structures. It's a subset of the space of smooth almost complex structures. I have the C infinity topology on it. Now, the fact that this subset of the moduli space is compact tells me that this space of regular almost complex structures that only cares about that is open. And it's also dense due to the argument I just did above. I can perturb any almost complex structure to one that achieves regularity for all of M good, not just the subset. So due to the above argument, it's dense. So all I have to do now is say the space I'm looking for, called J reg U, is the countable intersection of these J reg n's. And then I'm done, because that's a countable intersection of open dense subsets. So the rant that I will give you on this topic is that the Floor-C epsilon space is a very nice object, but you shouldn't take it too seriously. My personal opinion is it should never appear in the statement of any theorem. It should appear in lemmas, and it should appear in proofs of theorems. But just about any theorem you can prove about the Floor-C epsilon space, you can also prove about C infinity using this trick.
And you also get the fact that if you have two elements in J reg, they'll be joined by a regular homotopy.
Yeah, indeed. I mean, the argument works in more or less the same way if you want to study regular homotopies.
Can you explain this trick? Where did you get rid of that epsilon?
Yeah, where is epsilon?
Which epsilon? I mean, epsilon is a notation representing a space. So I guess the key point is the claim that this set of J's here is dense. So it follows, what I said here is that the set of J's that achieve transversality for me is dense in C infinity as a consequence of the fact that it's also a bare subset of J epsilon. This uses the fact that J epsilon has a continuous inclusion into C infinity. Right, so once I get density in J epsilon, I also get density in C infinity.
I mean, the Taubes' trick is sort of finding a compact space so that when it's compact, you can say the regular elements of the compact thing are open. So Taubes' trick gives you the openness. And then you take an intersection of open density, a countable intersection of open density.
Yeah, that's a good way of putting it. Yeah.
Excuse me, could you explain again why this JREC M is open?
So yeah, why is this open? So first of all, this space is compact because it's a closed subset of a compact space. Now, all right, suppose that this thing were not open. What would that mean? It would mean we've got some J that achieves transversality for every curve in this space, but we could also find a sequence of curves or a sequence of J's converging toward J that don't achieve transversality for every curve in the corresponding spaces here. But now, compactness tells you as the J's converge, the U's in these spaces also have a convergent subsequence. and they're non-regular curves converging to a regular curve. That's what's not possible because regularity is an open condition, right? That's surjectivity of a Fredholm operator. That's an open condition.
And can you explain dense again?
Okay. Did you believe me up to this point? So we get co-meager in J epsilon, which implies dense in J epsilon, and that implies dense in C infinity, just because J epsilon includes continuously into C infinity.
Well, you have to take over the union for all J fixes.
I don't.
Because
That's the part I.
No, J refs, rather, yeah.
Overall
Yeah.
J refs.
Yeah, right. I mean, exactly. So what this proves is for your original J ref, you can approximate J ref arbitrarily well in C infinity with a regular J. So a J ref was arbitrary. So that implies that the regular things are dense in C infinity. And dense in that is actually a stronger condition than what we need down here. Implies it immediately. Yeah.
So if I have a sequence in M and J, I could converge to something nodal, right?
No. A sequence in M and J will not converge to anything nodal because it is a positive distance away from the nodal part of the compactified moduli space.
But what if, I mean, there can be nodal things in M good, right?
No, there cannot be. Right. M good consists only of somewhere injective, honest J holomorphic curves. Yeah. I mean, it really seems like cheating, right? You're using the knowledge that this compactification exists and just saying, let's stay a finite distance, a positive distance away from the bad part of the compactification.
But for M of J, you kind of fix some asymptotics.
I don't have to, well, I assume non-degenerate Rabe orbits, but I don't have to fix more than that.
Well, to get, I mean, finite, uniformly finite over energy.
This is okay. Well, no, okay. Actually, here's a good reason why I want co-meager. What I really should do is do this whole argument just looking at holomorphic curves in a fixed genus and fixed relative homology class. And then say, having proven we have a co-meager subset for that genus and that homology class, now take the countable intersection of all those choices as well.
If you're just looking at maps whose domain is a sphere, so it would make it really simple, then this M and J, you can define it simply by giving a pointwise bound to the derivative. Just say that the derivative is bounded by some constant number.
That's a good point.
And then that means that no bubbles can form. I mean, it's equivalent to this. It's just a much easier formulation.
This is what you actually see when people use this in the literature. I mean, I'm using this formulation as a shortcut. But when you write this down in the literature, usually people write down a list of conditions that say things like the C1 norm of D, or the sup norm of du is bounded by 1 over n, or sorry, bounded by n. Also some condition about distance of u of x minus u of y divided by distance from x to y should be within bounds determined by m so that you stay away from the multiply covered curves. And you need something to keep you a positive distance away from nodal curves as well. So one can write down conditions like that which do everything for you without having to first prove Gromov compactness or SFT compactness, whichever, right? So the argument, in fact, you can do this for closed curves at least, you can do this in almost complex manifolds that are not tamed by a symplectic structure. You don't have to prove Gromov compactness first. You just have these conditions. You have elliptic regularity telling you C1 bounds will give you compactness, and so forth. Okay.
Can I ask one last time, why does injective inclusion imply density for C infinity?
So the claim is this. If I have a sequence of J's converging to some particular J in the C epsilon topology, then it also converges in the C infinity topology. So as soon as you know that you can approximate whatever J you want arbitrarily well in J epsilon, you have that's also true in C infinity.
And Chris, the bit of the proof that fails when you have, say, multiple covers is that hidden in the board hidden there, right? When you say that thing is positive, right? Because you can have that if you go around the point twice, say.
Right. Yeah, let's look at that again. So why does this fail for a multiple cover? I said choose an injective point, and we make this perturbation of, so we define y in some fashion on a neighborhood of u of z. Now, I want to do that such that this pointwise pairing becomes positive in a neighborhood of z. And I want to also know that it's not going to be positive in any other neighborhood somewhere else, which would happen if you had another point going through u of z. That's why this fails for multiple covers.
Well, it could be negative from multiple point. It could be negative somewhere else and then sort of cancel out.
Indeed. I can't conclude anything unless I really know that this is the only place where u is going through this region. How much time do I actually have?
5-ish minutes.
Yeah, so I would argue that this has been a sort of hybrid lecture and discussion session, and that the afternoon discussion session should be the same thing.
So you haven't used one still, right?
I've not used condition one. No.
The organizers approve.
Very good.
Yeah.
So.
Or maybe we shouldn't let everyone else know before.
So let me at least write down the statement of what I still need to get to in the afternoon. So hopefully we're happy now with transversality for simple curves in symplectic cobordisms.
Actually, can you maybe move the tab strict board down so it's clear out?
Mm-hmm. Okay. So in order to actually do SFT, we also need to understand transversality for curves and symplectizations. So that's the translation invariant J. Here's the theorem. So let's say now M is just going to be a closed odd-dimensional manifold. We've got a stable Hamiltonian structure. It induces our hyperplane distribution psi and Rabe vector field RH. And remember, we have from that a special class of translation invariant almost complex structures associated to the stable Hamiltonian structure. So theorem 3 says that there exists another space I'm going to call J reg that's a co-meager subset of JH such that for all J's in J reg, all J holomorphic curves with, how should I say this, that are somewhere injective and not everywhere tangent to psi are regular. So let's unpack this a little bit. First of all, we're working in R cross M. Okay? So it's a trivial symplectic cobordism, which means our map can be written in terms of a real valued function and a map from a punctured Riemann surface into M. I call those UR and UM. And there's really 2 points of difficulty about this theorem. First, the perturbations I'm making for J are no longer really local because I require J always to be translation invariant. So any perturbation I make near a particular point is going to affect what J is everywhere up and down from there. So that problem turns out to be relatively easy to solve. There's a technical lemma which appears in one of the mid-90s HWZ papers again that says if U is somewhere injective, then the injective points of the map UM from the puncture Riemann surface to the odd-dimensional manifold are also dense. Okay, I'm not going to prove this. Actually, I've not yet managed to understand the proof because I haven't sat down with it long enough, but I can tell you where to look it up if you want to look it up.
Do you need to ask finite energy or something?
Yeah, I always assume finite energy. If you want to hear about infinite energy curves and symplectizations, you have to speak with Joel Fish and not with me. So that's one thing. So I'm not going to be too worried about the translation invariance as long as I know that the map to M itself has an injective point. Then I can imagine I could do the same trick I did with a perturbation just supported near that point, and that's not going to mess anything up. But what I'm more worried about is the fact that, remember, what are the conditions that these J's must satisfy? Well, for one thing, J maps the unit vector in the R direction to the Rabe vector field. And the Rabe vector field is not ever changing in this picture. That's fixed by the stable Hamiltonian structure I started with. The only thing I'm allowed to vary is how J maps the hyperplane distribution to itself. So I'm doing perturbations of J on a subbundle of real codimension 2. And I need to know that those perturbations are going to be a large enough space to achieve transversality. And you might notice from the statement of my theorem that if you're not careful, this isn't true. There are, in fact, for certain stable Hamiltonian structures, J holomorphic curves that will not be made regular by any perturbation of this sort. Just quickly write down an example, and then it's lunchtime. Let's say M is S1 times W, where again W omega is a closed symplectic manifold. No, let's make it simpler than this. Let's just say sigma is a surface. So S1 times W, and say T is the coordinate on S1. Omega is an area form on sigma. And then this is the Floer homology example that I gave you yesterday, but just with the two-dimensional case. So to do Floer homology in a two-dimensional manifold, you would write down this stable Hamiltonian structure of the form big omega equals omega plus some Hamiltonian term, if you like, or just take the Hamiltonian to be 0 for now. Lambda equals dt. So it means that psi here is the foliation by these surfaces sigma. And if I'm perturbing J in this translation invariant class, I'm really only perturbing what J does on that foliation. So that means I'm looking at T-dependent families of complex structures on sigma. Well, for all such choices, there exist closed J holomorphic curves that look like map sigma to R times S1 times sigma by taking Z to constant, constant Z. And these will sometimes have negative index. Right. So there's an exercise for lunchtime. Convince yourself that if you were really allowed to take a fully generic perturbation of J, you would kill all these curves if the genus is large, because they have negative index. So it means the perturbations in this translation invariant class are not large enough to actually achieve transversality for everything. They don't for these curves. So that's why I have this extra condition. You have to just pay attention to curves that are not everywhere tangent to psi. Now, for the case that most of us care about most, psi is a context structure, and it's easy to guarantee that your curve will never be everywhere tangent to psi. Okay? So I'll continue with this in the afternoon.
So in particular, any cylindrical thing?
Any cylindrical thing. Well, these. This curve is asymptotically cylindrical. All of its punctures approach Rabe orbits. All 0 of them. Right?
Actually, you only need, I mean, genus 1 is, if it's a torus, it's good enough, because
Yeah.
you've only got one variation, and you're only allowed to vary in the S1 direction, not in the R direction.
Yeah, I wasn't gonna commit myself to a statement like this, but I think it's true. Genus 1 is already a contradiction to transversality. Yeah. Okay, I'm done.
Yeah, so why don't we thank Chris?
Thus far in this mini course, I think it's fair to say all the results I've been talking about are pretty well considered standard. And the proofs I've described are also using more or less standard methods. The title of the mini course has the word classical transversality results. What I mean by that is any result that you can express in the form for generic domain-independent, almost complex structures J, we have transversality for some particular class of J holomorphic curves. So that's allowed to include some methods which cannot be called standard, and that's what I'm going to talk about today. In particular, because everything I talked about so far, with one minor exception when I talked about automatic transversality, everything else makes the restriction that we're only talking about somewhere injective curves, which, of course, is a big problem if you want to define big invariants, such as Gromov-Witten theory or SFT. And to a large extent, you cannot really hope for classical transversality results to be true in the generality that you would need to define those theories. And Dusa already illustrated this briefly, and I'll reiterate that a bit in a moment. But there are situations when those results can hold, when you don't need to go to much more general frameworks, such as the polyfold theory, in order to define everything. If you do get transversality for your honest holomorphic curves, it can make your life easier because the Cauchy-Riemann equation is much easier to handle and carries some sort of natural geometric information that you don't necessarily have in whatever perturbed equation you're going to solve in a more general framework. So sometimes it just requires much more originality in your way of thinking to get what you need. Let me give you an illustration. So for today, I'm going to depart a little bit from the title of the course and not really talk about SFT. So I'm not going to talk about punctured holomorphic curves, but just closed holomorphic curves. Let's say sigma and sigma prime will be closed surfaces. Almost all of what I'm going to say can very likely be generalized to punctured holomorphic curves, but that's work in progress, so I'm not really going to touch upon it besides a few general ideas. I will just tell you about things that I know. So a multiple cover looks like this. I have a k-to-1 holomorphic branched cover from one Riemann surface to another. Assume k is greater than 1. Sigma prime is the domain of some J holomorphic curve into an almost complex manifold Wj, capital J. And then the composition of these two holomorphic maps gives me the multiple covers. So let's assume V is somewhere injective. U is now a k-fold covered holomorphic curve. And it'll be helpful to note that there's a relationship between the Euler characteristics of these two domains as they both figure into the index formula. So there's the Riemann-Hurwitz formula that says minus Euler characteristic of sigma plus the degree of the cover times Euler characteristic of sigma prime equals this quantity that I like to call z of d phi, because that's literally an algebraic count of the zeros of d phi. Or in other words, it's the number of branch points counted with the orders of branching, number of critical points of phi. And since phi is holomorphic, all of those count positively. So this is an integer that's always greater than or equal to 0. So we have this as a constraint relating the domains. If you've never seen the formula before, you can just think of it this way. D phi is a section of a certain complex line bundle, which you can easily write down. And then you can compute C1 of that line bundle. The answer is the left-hand side of this formula.
That's the hard way to understand that.
Not me.
Please.
Yeah, you can also draw some picture with, you can triangulate things and draw a picture of what branch points looks like. So maybe you prefer that. But it's very quick thinking of it as C1. This is, if I ever forget the formula, that's how I remember. So now let's write down the index formulas that we get from Riemann-Roch. So the index of V, so W, let's assume, is 2n dimensional, real 2n dimensional. The index of V, by which I mean the virtual dimension of the moduli space of unparameterized holomorphic curves that V lives in. So that's not literally the Fredholm index of the linearized Cauchy-Riemann operator, but it is, by basically what I explained before, it is that plus the dimension of the relevant Teichmüller space. Okay? So it's the actual dimension of the moduli space if transversality holds. And the formula is n minus 3 times Euler characteristic of the domain plus 2 first Chern class evaluated on the homology class of V. How does that relate to the index of U? So same formula with a different domain. Now, Riemann-Hurwitz tells me I can rewrite the Euler characteristic of sigma as k times Euler characteristic of sigma prime minus this count of branch points. And of course, C1 of U is just k times C1 of V, so I have 2 times that. And now I see sitting inside this formula k times the index of V, because there's n minus 3 times the Euler characteristic of sigma prime plus C1 of V over here. I just have an extra term, so I get k times the index of V minus n minus 3 times this count of branch points. So in particular, to be a little bit more concrete on what can go wrong with transversality for multiple covers, suppose that the underlying somewhere injective curve has index 0. So that's generically a rigid isolated object in its moduli space. And for generic J, it's also going to be stable under small perturbations of J, which means there's no way you can get rid of the multiply covered curve, since there will always be a perturbed multiple cover of your perturbed somewhere injective curve. But the index of U is then going to be minus n minus 3 times this non-negative count of branch points, which can easily be negative, at least if we're in dimension 8 or upward. Unless the cover is unbranched, that's going to be a negative number, right? Dimension 8 and upwards, that's precisely where we stop being able to assume that our symplectic manifold is semi-positive. So there we run into trouble. This is likely to be a negative number in general, but we see that we cannot perturb that curve away. The situation is actually even worse. If you think about what kind of curves we already know must exist in a neighborhood of U, there's not just U itself, there's the other nearby branched covers of the same V. And those come in a non-trivial moduli space in general. So the actual dimension of the moduli space of holomorphic curves near U, and when I say actual dimension, I'm not making the assumption that it's a smooth manifold or anything. It might not be. It might not even be a smooth orbifold, but it does contain a smooth orbifold which I can identify very clearly, namely the space of branched covers of sigma over sigma prime of the same degree. So we get at least the dimension of the space of k to 1 branched covers modulo reparametrization. And that's a very well understood moduli space. That's just another moduli space of holomorphic curves living in dimension 2, if you like. And you can compute the dimension from the Riemann-Roch formula as usual. The answer is 2 times the number of branch points. And there's sort of a geometric interpretation.
Riemann-Roch formula for that. So you can just see that.
This is my next sentence that you just interrupted. Right? There's a geometric interpretation of this because given a branched cover, you can find other branched covers nearby by moving around the positions of the branch points in the image. And those are not equivalent up to reparametrization. They give you different branched covers. And this is precisely the number of parameters you see by doing that. So this is basically classical. So we see that number is never going to match the actual index of U unless possibly the cover is unbranched, or what? Or if we're in dimension 2. But so what? We don't really care about dimension 2, right? So here it's fair to say transversality is generally not plausible for the multiple covers. I do want to make another observation about this, though. So again, the index of V is 0. So generically, by which I mean after possibly perturbing J, I'm allowed to assume that somewhere injective index 0 curves are immersed. Okay? Why is that? So I've discussed this with a couple of people since my last talk or discussion session or whatever it was. There was an exercise I posed about using automatic transversality to prove that in a 4-dimensional symplectic cobordism, generically an index 1 holomorphic cylinder will always be regular. And part of what you have to do to prove that is observe that whatever kind of holomorphic cylinder that one covers, if it's a multiple cover, is also going to be of sufficiently low index so that you can assume it's immersed. And then you can apply the automatic transversality criterion after you know that. So there's this general fact, which I don't have time to talk about in earnest, but one can show that if you take your usual moduli space, add a marked point to it, so that increases the dimension of the moduli space by 2, but now constrain that marked point by asking for the derivative, the first derivative of your map, to vanish at that marked point. So in general, that decreases the dimension of the moduli space by 2n. So the upshot of that is, for generic J, the space of holomorphic somewhere injective curves that are not immersed may be considered to be of codimension 2 minus 2n compared to the larger moduli space. So that means if my index is 0, I can assume that that space of non-immersed curves is empty. Therefore, this one's immersed. Okay? So I'm not going to say more about that. Let's just accept it for now. It's sort of it's a J-holomorphic fact analogous to the standard differential topological fact that you can perturb smooth maps to be immersed, right? Given the right dimensional conditions, at least. So we have this. Now, that means, let's look at the normal bundle. I've got.
Can you at least say why there's more to say than what you just said about why this statement is true?
Yeah, because you have to work out the details. Go ahead and try it, and let me know how it goes. Come on. Okay. So the normal bundle is not the generalized, but the usual definition of normal bundle here. Okay. That's what its C1 is. The generalized normal bundle of U is very easy to describe. Right? U is not immersed because there can be branch points, so there are critical points of U. But of course, the generalized normal bundle of U is just going to be the pullback of this normal bundle of V. So that's 2k times that number over there, C1 of V minus Euler characteristic of sigma prime. So remember I talked last time about restricting the linearized Cauchy-Riemann operator to the generalized normal bundle. That also gives you a Cauchy-Riemann type operator on a bundle of rank 1 lower. Its Fredholm index is given directly by the Riemann-Roch formula. Let's see what it is. So DUN is the restriction to the normal bundle. And Riemann-Roch tells me, well, the rank of this bundle is n minus 1 as a complex bundle. Times the Euler characteristic of the domain plus 2C1, the generalized normal bundle. So Riemann-Hurwitz tells me what that first term is. Okay, we have this extra term counting the number of critical points. And then 2C1 and U I've just written up here. It's there we go. Am I missing something? People are saying there's a K missing, but where?
No, there shouldn't be.
There shouldn't be a K.
Yeah, the last one.
The K's missing.
Well.
From the first line, you have 2 times the question path.
Yeah, but that's V and this is U. Right? That's why there's the K. No, I think this is okay. I'm doing this a slightly more roundabout way than I planned accidentally. So I've got K times n minus 1 Euler characteristic minus another 2 of the Euler characteristic. Plus twice C1 of V, then minus n minus 1 times count of branch points. This is fine, because this number in the brackets here is 0, because I assumed that V has index 0. That's the index formula. So I'm just left with minus n minus 1 Z of d phi. So what I notice about this is, unlike the index of U that I wrote down, just looking at the normal operator, there's some predictable pattern. This number is always non-positive. which means it's conceivable that this normal operator might actually always be injective. And that's something geometrically meaningful if it's true. So I'm going to actually state this as a conjecture. About a year ago at this time, I was calling it a theorem, but then an error was discovered in that proof. So this is a conjecture that says, so for generic J, all multiple covers U of somewhere injective index 0 curves V have normal Cauchy-Riemann operator injective. Which has a nice consequence if it's true. What that actually implies is all of the other curves in the neighborhood of U are precisely the ones you already know about. They're just the other multiple covers of V, right? So I'm saying this result would give you a precise description of the moduli space of curves near U as having exactly this dimension of the space of branched covers.
Is that strong enough to get PPS integrality for large people?
That would be the intention, right? So the intention of a result like this would be to prove something like the Gopal-Kumar-Vafa conjecture, right? So the reason why this kind of thing is supposed to be interesting is that it means in certain settings, if you want to compute Gromov-Witten invariance, you really only have to understand the somewhere injective curves. And the rest of it, of course, the multiple covers are not regular in the usual sense, so you have to do some kind of perturbation if you want to actually count them. But there's a standard way of doing this with inhomogeneous perturbations to the Cauchy-Riemann equation, and you can predict the count that you'll get because you see the entire moduli space in terms of the space of branched covers. It has an obstruction bundle, and you can compute the Euler class of that obstruction bundle. That will give you the answer. Right? So this has nice corollaries in Gromov-Witten theory.
What was the answer to my question?
I think the answer to your question was yes. Yeah. Yeah. Yes.
I'm not really sure how to interpret the index of this of DUN.
Right. The main thing I want to say about it right now is that since it is generally negative, the operator can be injective. And what I really want to explain is how you interpret the fact that that operator is injective. Okay? So if the kernel of this operator is trivial, think about it like this. The following is the scenario you don't want. You don't want to have a sequence of curves that have different images from U converging to U. Okay? My claim is that all the sequences of curves that can converge to U are of the form V composed with some other branched cover. So they all have the same image. Now, if you have a sequence of curves with different images converging towards U, you can do this trick where you look at that as curves living in the normal bundle of U and rescale that normal bundle so that as the curves approach, you rescale so that you see them not actually approaching but staying in some bounded subset of the normal bundle. Apply Gromov compactness to that. That sequence is going to converge to some generally nodal holomorphic curve, which will have some component that you can interpret as something either in the kernel of this operator or in the kernel of some related operator corresponding to a branched cover of lesser degree. So if you know that these kernels are all trivial, that precludes this scenario. Right? So it says really that the space of branched covers, or the space of U's that are branched covers of V, is an open subset of the whole moduli space. Okay. This is all speculation. I mean, the argument that I just described can be made fully rigorous. But of course, the conjecture is only a conjecture, right? We don't know if this is true. So I do want to talk about a special case of it, which we do know. Yes?
Can you give an example when the hypotheses of conjecture aren't satisfied where the desired result isn't true? Multiply covered curve that you can approximate by curves with different images.
I'd have to think about that a little bit. I mean, I certainly could come up with examples given enough time where, in particular, there's hardly any conditions here. The main condition is just that the simple curve has index 0. So in situations where that's not true, right, the possibility of a sequence of simple curves converging to something multiply covered is always something you have to worry about. You usually have to make some effort to avoid it.
Doesn't Taubes have some examples when he counts tori and he has multiply covered tori that sort of generically branch off double covers in one family?
I'm going to talk about that a little bit, but I don't think it's an example of this phenomenon. Okay. It's much nicer than that.
Richard Hein has some nice example where you need genericity there.
Okay, I'm not aware of that. Okay. So here's an actual theorem, which is one of the cases of this conjecture. And this is in a joint paper that I wrote with Chris Gehrig last year. I'm going to make the statement a little bit unnecessarily more complicated than I need just to illustrate how different it is from the results we talked about so far. So let's say fix an open subset U in our closed manifold M, closed symplectic manifold of dimension 2n. And fix also a tame, almost complex structure, J fix. Then I will say there exists a co-meager subset J reg living, as you'd expect, in the space of all j's that are omega tame and match J fix outside of this subset. Such that for all j's of this class, all unbranched covers, U of somewhere injective index 0 curves, consider to call it V, contained in the perturbation domain are regular. So remember, if I'm talking about unbranched covers, then the disaster scenario I described with this index relation doesn't happen. That's the case where index V equals U implies index U, index V equals 0 implies index U is also 0. So in that case, regularity in the usual sense is plausible numerically. And I'm saying for generic J, it actually happens, at least if we're looking at curves contained entirely inside this perturbation domain. That's one major difference with the theorems I explained earlier. I'm not saying we get regularity for all the curves that intersect or have any point mapping into the perturbation domain, but they have to be contained in it entirely. So we'll see why that seems to be necessary. I don't know if that condition can be dropped. I certainly don't know a way of dropping it.
Is there any reason you can't just take U to be the whole, like all of it?
No, you can certainly take U to be the whole manifold, right? But if you wanted to just do perturbations in some subset, then you have to restrict yourself a bit.
Do you ask that U has to have like compact closure or something like that?
Well, U is closed. Yeah. Or sorry, U. M is closed. Therefore, U has compact closure. Yes. I mean, I could also allow M to be not compact, and then I would indeed have to require that U has compact closure. That's a good question, in fact. Okay. So I'm not going to explain the proof in quite this level of generality, but I'm going to explain a case of it, which is somewhat older than our result, but somehow very badly known or badly understood. So in the case n equals 2, so it's just dimension 4, and where both domains are the torus, and the underlying simple curve is actually embedded. So this is what Dusa alluded to with her question a moment ago. This was done by Taubes in 1996, a paper in Journal of the AMS. The proof there is kind of hidden. In fact, when I went back to it last night to figure out where it was, it took me a while. And it's very sketchy, but somehow the ideas in it are extremely potent. So, of course, this means we're getting regularity for multiply covered holomorphic tori that are covering embedded tori. Taubes needed this because his definition of the Gromov invariant actually counted those things, and it did it without doing abstract perturbations. It did it for generic J. So in this situation on the torus, there are some convenient things. The fact that V has index 0 means that its normal bundle has to be trivial. So I can write normal bundle of V is going to be identified with a trivial bundle over T2, complex line bundle, and U similarly. And a Cauchy-Riemann operator, if I write it in those terms, just looks like the usual d bar operator plus some 0th order term. So here, by d bar operator, I mean literally just partial by s plus I times partial by t, acting on complex valued functions. And A is, say, a C infinity map from the torus to the space of real linear endomorphisms of C. That's what a 0th order term looks like. And then the pulled back normal operator is literally the pullback of that. So the normal operator for U is going to be the standard d bar plus this 0th order term A composed with the cover of phi. So just a few general points before I really get into the argument. It suffices to show the following. Suffices to show that for all J, of course, of the tame class I'm thinking about, V is a J holomorphic embedding of the torus into this perturbation domain, and U equals V composed with some cover phi. Phi is necessarily unbranched since it's a torus covering a torus. Then I want to show that I can perturb J to J prime such that V is still J prime holomorphic, but the normal operator for U becomes an isomorphism. Okay, defined with respect to the perturbed almost complex structure J, J prime rather.
Can you explain one more time how to think about the normal operator geometrically?
Right, its definition is very simple. You take the ordinary Cauchy-Riemann operator, which is defined on the pullback tangent bundle. You restrict it to sections of the normal bundle, and now you get some section of a larger bundle that you don't want, but also has a projection to a corresponding normal part. So it takes you to some section of the bundle Hom bar of T sigma to U star TW, TM, whatever it's called. There's a normal projection in that as well. It takes you to Hom bar of T sigma to normal bundle. So you just compose the Cauchy-Riemann operator with that normal projection.
But so to speak, in terms of deformation, sort of, maps, the tangent bundle, I mean, I take arbitrary deformations of my map.
Yeah. Okay, yeah, there is another nice way to think about this. So there's an alternative way of describing a neighborhood of a curve in its moduli space that I didn't talk about. If the curve is immersed, specifically. So if the curve is immersed, one way of describing all the other curves nearby, let's actually write this a little bit. So U is immersed. All the other curves nearby can be assumed to be of the form exp U H for some H section of the normal bundle. Okay? Now, in fact, that's going to hit a unique parameterization of every nearby curve in the moduli space, but you don't get to choose what complex structure you have on the domain at all. So what you have to do then is not actually look for nearby maps of this form that solve the Cauchy-Riemann equation with respect to some specific J, but these are all going to be immersed also. So just look for nearby maps like this whose tangent spaces are J invariant, so that automatically you can pull that back to some complex structure on the domain. You don't get to prescribe it. So that's another way of seeing all of the holomorphic curves in the vicinity of this one immersed curve. And, well, you can write down some nonlinear operator that does that for you. Its linearization is essentially this normal Cauchy-Riemann operator. Right? That also tells you why it happens that the Fredholm index of the normal operator is the same as the dimension of the moduli space in the immersed case.
That's basically because if you perturb in the tangent direction, then you just are reparameterizing basically.
Right. Perturbations in the tangent direction are sort of not meaningful for studying this moduli space because this is giving you reparameterizations of the same curve. Okay. So I don't know if everyone had a chance in the meantime to think about why what I just said here is true. It suffices to show, given a curve and a multiple cover, you can perturb J to one that makes that specific multiple cover regular in the sense of the normal operator being an isomorphism. So this is an exercise using the Taub's trick that I explained last time. Right? You can exhaust the space you're interested in with a countable union of compact subsets, in this case finite subsets even. So as long as you're able to achieve transversality for each of those subsets, then you can find some set of J's that's a countable intersection of open dense sets that does everything you want. Okay. So that's all I'm going to say. This is a version of the Taub's trick to get you from there to the result we really want. The other thing I'm going to say is we can reduce this problem to something that's really only involving linear Cauchy-Riemann type operators on an abstract vector bundle. Because I can say for all zeroth order terms A prime, so zeroth order term is just some C infinity function valued in the space of real linear maps on C. We can find J prime such that J prime equals J in the tangent directions on the curve V. So T sub V is what I was calling the generalized tangent bundle before. Literally, that just means the image of the differential of V. And we can also say J prime equals J outside some neighborhood of the image of V. But the normal operator for V expressed in this trivialization and expressed with respect to the perturbed almost complex structure is d bar plus a prime. So I'm only saying here, give me any perturbed Cauchy-Riemann operator you want in the space of all real linear Cauchy-Riemann operators. I can find a perturbed J that realizes that operator for you. And this is not terribly deep. Actually, in the embedded case, when V is embedded, this is fairly easy to prove. It's just a matter of choosing the normal first derivative of your perturbed J in the right way to produce the right zeroth order term. One can also do it in the immersed case, and that's a bit more painful. But I'm not going to talk about that. Okay. So let's also take this as given and just look at a problem involving Cauchy-Riemann operators on line bundles.
Sorry, I have a question about this thing. I don't understand in the middle of the first line, such that J prime is equal to J on T sub B is equal to 2 dV.
The image of dV, in other words, the tangent spaces to the curve.
Oh, I thought that was the index of the I see.
Yeah.
Great.
Any other questions? All right, so here's a claim. And I'm even going to label this one an improbable claim. Because when I first saw this in Chaub's 96 paper, I had no idea why I should believe this is true. And I'm still not sure I can explain to you why you should believe this is true, but I can prove it. So here we go. Let's suppose D of the form d bar plus A is a Cauchy-Riemann operator on the trivial bundle over T2, trivial line bundle, and B is a bundle map on that trivial bundle, which I'm going to assume is a complex antilinear bundle isomorphism. So the two key properties are it's complex antilinear and it's a bundle isomorphism. So given that the bundle is trivial, it's obvious that you can do this. This is more or less equivalent to saying B of Z acts on a vector eta in a certain fiber by some complex valued function beta of Z times complex conjugate of eta, where this complex valued function beta is assumed to be nowhere zero. So it's mapping into C star. Okay? So that's the assumption. I want to just mention quickly, if I were not working on the torus, but with an unbranched cover with more general domains, sigma and sigma prime, the assumption that the index of the simple curve is 0 allows me again to do this. Then I would be able to find a complex antilinear bundle isomorphism between the relevant bundles, even though they're not trivial. That's actually equivalent to the fact that the index of the simple curve is 0. So that's something also that is easy to check. Now, the statement will be that I can define a perturbed operator d tau as tau plus a real parameter times this extra bundle map B, treated as a zeroth order term. That is an isomorphism for all tau real numbers outside some discrete subset. Okay? So this is one way of perturbing a Cauchy-Riemann operator that might not be an isomorphism and making it into an isomorphism. In particular, what you need to notice about this perturbation is it doesn't care at all about symmetry. I require this extra term B to be a complex antilinear isomorphism. I don't require it to be anything else. If my bundle is a pullback of some bundle that's defined by a simple curve, but I have been looking actually at the normal operator on the multiply covered curve, I can do a perturbation like this just by changing j along the simple curve. Now I pull that back to the multiple cover. My perturbation of my operator is going to be invariant now under deck transformations of the cover. This claim does not care. Okay? Where symmetry messes up the usual argument in this, this is the reason why I need somewhere injective in the usual arguments. Symmetry ruins this Sard-Smale argument. This is impervious to that. So I need to convince you this is true.
Sorry, like if it weren't an isomorphism, would it still preserve the index of the original B?
But it's a compact perturbation of the operator. So yeah, this doesn't change the index. Right? So basically all the Fredholm operators in this talk have index 0. So they're either isomorphisms or they have both kernel and co-kernel. Yeah?
Can you remind me or tell me what's the upshot? So suppose we have this, how are we gonna use it?
Right, so if we have this, that means I can find, so if I have my given j and my given cover, which is maybe not regular, I can find a perturbed j that perturbs the normal operator along the cover in this way, and therefore makes that curve regular. So, first step. Oops. This one parameter family of operators d tau is injective, which of course, since it's index 0, implies it's an isomorphism for all tau sufficiently large. So this step is interesting because I'm quite convinced that this argument couldn't have come from somebody who was mainly a symplectic topologist. It had to come from a gauge theorist. In particular, if you're familiar with Taubes's work relating Gromov invariance and Seiberg-Witten invariance, you'll notice a parallel here. There's something that Taubes does in Seiberg-Witten theory where you write down the Seiberg-Witten equations with this perturbation term depending on a real parameter. And you can prove that for topological reasons, if you make that parameter very large, you don't have any solutions. Or you do have solutions, but they're converging in the sense of currents to holomorphic curves, something like that. So this is going to be a much easier version of that. And it's an argument that I've never seen anywhere else in symplectic topology. So let's say we'll think about, well, I haven't really specified at all what Banach spaces I'm working with. Let's just, to make my life easy, let's choose Hilbert spaces and say the operators are going from H1 to L2. So let's suppose I have some non-zero element eta in H1 on the torus. And the idea is to operate on that with d tau and look at the L2 norm squared. So d tau is a sum of two terms, which means I can expand this L2 pairing, and I'll get three terms. I have d eta, L2 norm squared, plus tau squared times L2 norm of the perturbation b, which I'm writing here as beta times eta bar. So let's write it beta eta bar, L2 norm squared. And then there's a cross term. I'm assuming that my inner product is real valued because the linear operator is real linear, not complex linear. So I can use a Hermitian inner product on the trivial complex line bundle, but then I have to take the real part. So this is going to look like 2 tau times the real part of the L2 inner product of beta eta prime with d of eta, let's write that out as d bar eta plus a eta. Okay? So a few observations about this. Of course, this first term is non-negative, obviously. The second term, since I assumed that B is a bundle isomorphism, which means this map beta is nowhere 0, I can bound this term from below by the L2 norm of eta. So this is greater than or equal to some constant C1 times the L2 norm of eta squared. And that's all I need to care about that term. Over here, I really have two terms in the cross term. So let's look at the more harmless one first. The pairing of beta eta bar with A eta. That also is clearly, its absolute value is bounded above by another constant times the L2 norm of eta squared. And I have to worry a little bit about, the other part of the cross term. So I need to work a little bit to estimate that properly. So I'd be much happier with that term if it didn't involve a derivative of eta. So you have an L2 pairing of something with something else that's a derivative. What do? You can integrate by parts. Let's see. Real part of inner product beta eta bar with d bar eta is literally the real part of the integral of the conjugate beta bar times eta times d bar eta integrated over T2. Now use the Leibniz rule and say that's integral of d bar of the whole thing, beta bar eta times eta, minus the integral of d bar beta bar eta times eta. Integrating d bar of something over a closed manifold would give me 0 due to Stokes' theorem, or probably even reduce that to the fundamental theorem of calculus. That's 0. Over here, I can expand a little bit further and say minus real part d bar beta bar times eta. No, still minus. This is one of those arguments where if you get one sign wrong, you're really dead. Beta bar d bar eta. OK. Hopefully, I got the signs right. And I'm missing an eta. Yeah, here. Thank you. That's important, because I want this term to be the same as that term that I had on the left-hand side. So I can put this last term on the left-hand side. So I have twice that equals this. So the thing I'm trying to estimate actually equals minus 1/2 real part integral of d bar beta bar eta times eta. And I don't really have to care about the details of this anymore either. I just want to say the absolute value of all this is now less than or equal to some other constant times the L2 norm of eta squared. So I put that all together. Now this whole thing.
Sorry, Chris, are you somehow saying that d bar operator is self-adjoint, or?
No. I am saying that if you take a complex valued function on the torus and integrate d bar of it over the whole torus, you will always get 0. And that you can prove that using Stokes' theorem.
But that means you're just throwing d bar up from one term onto the other.
Yeah.
And that's an L2 inner product. So
No. So, I mean, it was an L2 product to start with, but I wrote it as a product of complex numbers over here. I took conjugates of the terms on the left. Yeah. So this is an integral of a complex valued function that's expressed as a product of complex valued functions. Right? It equals that L2 inner product.
It's just the real part. Okay.
Right. So I'm defining my L2 product to be the real part of this integral. So
so when you write eta times eta, what do you mean? You've got eta's a
complex number.
Eta's a complex number, so it's just the square of that.
Yes.
It's a function. Right?
Yes.
And you've got some measure on T2 that you're integrating.
the usual one, yes. So these are good questions, and they kind of allude to the fact that one can do all this in a much more general setting, but it causes a bit more of a headache, right? So this is not a uniquely low-dimensional phenomenon I'm describing, even though I'm describing a low-dimensional proof. You can do it in higher dimensions. You can also do it on more general domains. It just requires several extra steps that I don't have time for. So to summarize this d tau of eta L2 norm squared is now greater than or equal to some constant, which I'm going to change the name of the constant, C1 prime times t squared minus another constant C2 prime times tau, tau squared tau times L2 norm of eta. And that's the proof. If eta is non-trivial, then this cannot be 0, as long as tau is sufficiently large. Okay?
Why did you need to evaluate this last one? Why couldn't you immediately say let's take tau very big?
Which stuff?
The first one goes as tau squared, and then the second is small.
First one, yes, goes like tau squared. I mean, the main difficulty in this argument was that I had to get control over this term that has the derivative of eta in it and relate that to just the plain L2 norm of eta. That's what the integration by parts is for. Okay. And that's also where I used, I mean, you may not have noticed it so explicitly, but that's where I used the assumption that my perturbation term is a complex antilinear perturbation. So specifically because it appears in there as beta times the conjugate of eta. If I didn't have eta bar on the upper left, this argument wouldn't have worked. That's as close as I can come to giving you an intuitive reason to believe this. I'm sorry. So, yes?
And the constants, they're like C3 and C2. C3 is like the norm of del bar beta bar.
It's whatever is convenient. There is one. Do you believe that there is some constant that makes that true? You stare at it a little bit longer and you'll be fine. All right. So I'm almost done. I have one more bit of magic to pull off to finish this proof. And that's a bit of analytic perturbation theory. So I won't have too much time to... How much time do I actually have?
3 minutes.
Yeah. That's always the answer, isn't it? Analytic perturbation theory. So what I'm about to say can be done in the real analytic category, but I don't want to because I'm a little bit allergic to the real analytic category. So instead, I'm going to work in the complex analytic category and complexify my operator first. My operator is only real linear, even though it's acting in a complex vector bundle. So what I can do at the expense of having 2 complex structures in the picture instead of 1 is I can complexify the domain and the target of the operator and consider the canonical complex linear operator, the extension of that to the complexification. So, more precisely, so we've got d tau is a real linear operator from some space of complex valued H1 functions to complex valued L2 functions. Let's take, actually to be more precise, we can say this is H1 functions from S1 to R2. And calling it R2 instead of C will help avoid some confusion coming up as I'm about to complexify it. Sorry, yeah, T2, not S1. I have a nasty feeling it even says S1 in my notes. That's not so good. So if we complexify, this becomes an operator I'll call d tau c from, call it h1c, which you can think of as, well, the tensor product of this Hilbert space with C, which is equivalent to the space of h1 functions from T2 to C2. And it's going to map that to corresponding space L2C. And it's complex linear. And what I can do now is allow my parameter tau to be complex instead of just real. So now, the map taking tau to the operator d tau is a holomorphic map from C to the space of Fredholm index 0 operators, complex linear, from H1 complexified to L2 complexified, which of course is an open subset of the space of all bounded linear operators, complex linear, between those spaces. So this is just a complex Banach space. I have a map from C into that Banach space. It is easily seen to be differentiable with respect to the complex variable tau, right? In fact, it's an affine map. So that's a holomorphic map into this open subset of Fredholm index 0 operators. So the last step is then to observe the following. The space of non-invertible operators so operators that are not isomorphisms sitting inside this space of Fredholm index 0 operators is what we call an analytic subvariety, a complex analytic subvariety, which means locally you can express it as the zero set of some holomorphic function on that infinite dimensional, so open subset of an infinite dimensional complex Banach space. But that function is valued in something finite dimensional. It's valued in C, in fact. So what we end up with is the set of all parameters tau in C with the property that the complexified operator d tau c is not an isomorphism, looks locally like the zero set of a holomorphic function from C to C. That's why that set is discrete. We already showed that it's not right? It's not everything, because for very large tau, the operator is an isomorphism. So once you know then that the zero set must be discrete, you're done. And then, of course, you have to think a little bit about relating this statement about the complexification to the original real linear operator. That's fine. Basically, you can convince yourself that if tau is real, then the complexified operator being an isomorphism implies that the real linear operator is an isomorphism. So I was going to prove this lemma. In fact, I was going to say other stuff after that, but there's no time. So if you want to know the proof of the lemma, I can tell you whenever, if my voice holds out.
But not now.
But not now. So let's have lunch.
Are there any other questions?
Well, when you say it's a discrete set, do you really mean it's a finite set? I mean, it can't accumulate on zero, can it?
Yeah, so I don't I don't know what happens for other large complex parameters that are not necessarily in the positive real line. It's probably.
Thinking, I mean, you were talking about, I mean, your main interest was in the zeros when tau was real, right?
Yeah.
And near zero, because we're making a little calculation.
This is why I haven't thought about the answer to your question very much. So it's probably true.
But if you're saying a zero set of a holomorphic function, they're isolated, aren't they?
They're isolated.
They're isolated.
Yeah.
So in other words, if it's zero, then there's a whole little neighborhood where it's not zero.
Correct. There's a whole neighborhood where it's not zero.
It's discrete. Well, oh, I see. A discrete including zero. Right. Okay.
So, please repeat what coming up with just to complete the picture. So, it's all this d tau, and this is all these, the c is the b, this a and b, get d tau, all they are kind of fitting to the picture of the complete picture itself. Operator corresponds to the picture.
So, okay. My goal, I had a specific normal Cauchy-Riemann operator for this multiply covered curve. So this is what, in this abstract discussion at the end, I'm calling just plain d. And then d tau becomes just some perturbation of this normal operator, which corresponds to some specific choice of perturbation of the almost complex structure in the neighborhood of the curve.
All right, so we're going to reset the clock and restart at 2. Have a nice afternoon. Let's thank Chris again.